Hi everyone, welcome to the companion notebook for the recitation of homework workflow. So in this notebook, we're going to train a simple MNIST classification network using PyTorch. So we'll go ahead and install the package that we're going to need. But before we do anything, I want to make sure that all the sales outputs are cleared. So yeah, I'll go ahead and start the package starting from touch summary. And then after installing this package, it's recommended that after you install any package using pip, you restart the runtime. So please remember these like small things. Sometimes it can run you into bugs. Yeah, so after I do that, I'll import all package that we need from PyTorch, Torch Vision, Matplotlib for visualization, Torch Summary that we installed previously, Scikit-learn metrics that we use to calculate accuracy, and there's also NumPy. Sorry, Matplotlib is here too. Yeah, so I'll run this cell again. And after this, we're going to create our data sets. So MNIST that we use is provided in PyTorch dataset in Torch Vision specifically. So I'll go ahead and download the trend set and the state set. But as a matter of practice, we also split the trend set into validation sets as well. So validation set will be 20%, and then the actual training set will be 80%. So we're also going to create the data loaders. So data loader are what we use for training neural networks usually. So so the most important thing to keep in mind there is that when you're creating data loader is you specify your data sets and then you specify the batch size. So batch size is hyperparameter. So here we are using 64, but this roughly depends on your hardware. So you can use as much as you want, as much as you want, as long as your hardware can support it. So we also shuffle the training set. This is a really important. So the training set, when you're creating data order, please shuffle the image, and also don't shuffle the validation and test set. This is important. So after that, we download the data and we create our data loaders, and then we can try to visualize how our dataset look like. Let's visualize the dataset. So you can see that our datasets are um, digit basically. So we are trying to build a network which can take a digit and then recognize its label. So for example, if the input image is 8, the network should be able to recognize that this is 8, should be able to output 8 as a digit, sorry, as a label. And if the input is 0, then the network should be able to recognize that this is 0, basically. Yeah, so you can learn more about the data sets. This is a black and white data set because we have one channel. Um, this is the data shape. 64 represent the batch size, and then 1 it's because our image are gray, and 28 by 20. So this is 800 basically. And yeah, so we're going to build a simple network for classifying digits. So the input size is 20 by 20. You might be wondering why we just set our input size to 20 by 20. This is because the kind of network that we're going to use for this notebook is multi-perceptron. So multi-perceptron, they take a one-dimensional input. So if you're going to, we can't feed the whole image to multi-perceptron. So we have to flatten an image. So if you have an image of 28 by 28, if you flatten that grid of pixels, you end up with a one-dimensional vector of size 28 by 28. Yeah, so this is why our input is set to 28 times 28. The height and size, this is hyperparameter that you can tune. So for now, we just use 1024. And then the output size is fixed to 10. This is because we have 10 digits that we are classifying. So this must be 10. So our model is a pretty simple model. So we have one hidden array, and we're using ReLU as nonlinearity or activation function. ReLU is probably one of the most popular used activation, but there are many activation functions that you can use, such as zero. So you can use whatever I want here. This we are trying to really like make a simple network, but you can experiment with whatever you want. You can add more hidden layers, you can change hidden size and see. Yeah, and then we run the cells, and after running the cell, after creating a model, normally we also create things like optimizers and loss function. So as optimizer, we are going to use Adam here. There are many other optimizers that you can use, such as stochastic gradient descent. But don't stress too much about like optimizers. Just choose whatever like you can start with. So Adam is like a very good starting point. So and then our loss function is cross entropy. So cross entropy is pretty specific to this task. So for most classification tasks, you're going to use cross entropy as the loss. But criteria or loss function really depend on the task. While things like optimizers, you can experiment with almost every over optimizer and see what works best. So I will run this set as well. Now we're going to write helper function for training and evaluating the model. So our train epoch take model, then we take optimizer, then we take criteria or loss, and then we take data loader. The very first thing you should do when you're going to train a model is to put the model into the training mode. This is basically to tell PyTorch that, hey, like we are going in training mode, so be ready and be ready to start training. Yeah, so please like really make sure that your model is in training mode before you start training. And so we will also accumulate the training gross and also create lists, these two lists for true labels and prediction labels. So I'm going to iterate through our data loader. We send image and labels to device, and after that, we are going to feed the image to the model. So note that we need to flatten the image first. As we say that MLP expect the input to be a single dimension or basically a single vector. So we need to flatten um, the, the input image, and then we calculate the difference between the model output or the prediction and the labels, and then we basically accumulate the training loss, and then we find the predicted labels, and then we continue, and then we return. So this function will return the train loss and train accuracy. So I will run it. A var function is pretty much the same as train function with few difference. So in a var, we have to make sure that our model is in a var mode. So if you don't do this, most likely you won't see any error, but you will override or overwrite the gradient. So please, when going to do a var, make sure that your model is in a var mode. Also accumulate train rows, and then we have the same list here for true labels and predicted labels. So we iterate through the data loader, we get image and labels, we make sure that we are in inference modes, we compute the logits, the same thing, we are flattening the image, then we pass the logits and labels to the loss, and then we accumulate the loss, and then we find predicted labels and true labels. And after this, we return the var loss and the var accuracy. I'll run this cell as well. So now that we have the helper function for training and evaluating our model, so we can start to train it. So I will train for 15 epoch. It's really simple model, so it should train fast. And yeah, let me run this. So what we're doing here is that so we are training for 15 epochs. For each epoch, we are doing a forward pass, and we are doing forward pass, um, and then we get the train loss and we get the train accuracy. We append the train loss and train accuracy to these lists. We are basically using these lists. We use them later, like for evaluating the performance of the model, for realization kind of things. Yeah, so and then after doing the forward pass, we also evaluate the model for each epoch, and we do the same thing. So then we print the train loss, train accuracy virus, and then the var accuracy. So I'm going to run this cell. But before I run this cell, I think it's important that we also keep track of the epoch. So I think it's best if we just track the epoch as well. Yeah. Let's say something like epoch, epoch, and we do this. Yeah, this will work fine. Yeah. So I'm going to run this here. Our training for 15 epochs. It should be fast. So you can see epoch 0, train loss, train accuracy, var accuracy. We are training for 15 epochs, so we'll have to wait for this. So while we are training, so maybe we can try to look at the subsequent section. Hopefully it's not going to be confusing. So basically, after you have trained your model, the next step is to usually evaluate the prediction. So it's usually like, yeah, visualize the model performance. So it's important that you do this because when looking at number like this, so you really can tell how the network is doing. I mean, like reading Raws and then accuracy, it really doesn't make sense until you plot them. So just to get you ready for the next section, yeah, like if you're reading the raws, like 0 point, like it just doesn't make sense. It's too much numbers for the brain. So that's why it's important that we visualize um, the the model output. You can use things like weight and bias for tracking your training. And I think you will see one of the station will be about weight and bias, and it will be the thing that we use for almost every assignment. Um, you can also use TensorBoard inside the notebook, or you can use like really simple thing, just plot the rows and accuracy using Matplotlib, which we'll do here. But again, like for most projects, you're going to be using uh, nice tools for tracking model. Yeah, so you probably use weight and bias, and you see it in almost most assignments in this course. You'll be using weight and bias. So our model is on epoch 10. We are about to be done, just 5 more epochs. Um, 5 more epochs. Again, like this whole numbers doesn't make sense, so we need to plot it and see. 4 more epochs to go. We have 2 more epochs to go. Um, okay, we are done. So yeah, like as I say, like these numbers doesn't really make sense. So to see how the network is performing, let's visualize the model. So we're going to first visualize the training and validation rows. Let me do it. Yeah, so you can see that our network is really overfitting. So there are many reasons why a network could overfit. So the most common is usually about the dataset. So like we have like this very simple dataset. We are not doing augmentation or anything. So yeah, like if you probably augment the dataset, then the network would probably not overfit. Um, and so we can also try to visualize the training and validation accuracy. It's the same thing. So like the training is fine, but again, the validation, you can see that it's not improving. So yeah, most likely we are overfitting here. So here, the best action to take here would be to augment the dataset or to even add more datasets. So after visualizing the prediction, if you are happy with your network, you can test. You can test it on unseen data. But it's important to know that you test your model on unseen data when you believe it's really good enough. So this network is not good enough in this case, but we are still going to test since we are doing it for the purpose of this station. But in the practice, if you build a model, you train it, and then you evaluate it, you see like it's not really doing well, you don't learn it on your test set. So you have to improve it before you can pass it to your unseen test set. Otherwise, you are leaking your test set to the model. If you are like training, evaluating, then like evaluating on test set. Yeah, so we do this for the purpose of this recitation. And as you have noticed, the eval function for that we use in training model, it's the same we use for testing the model. So it's meant to be the same. And yeah, so we are done. So I invite you to really like um change things as much as you can. Play with things. Deep learning, like in deep learning, most stuff are really like not specific. There's no single best batch size. There's no single best optimizer. There's no single best neural network. There's no single best architecture. There's no single best running rate. So it's really all boiled down to experimenting with things. So I invite you to experiment with things and change things and see what works, what doesn't work. So we also have exercise for you. Yeah, so like the steps we covered here are pretty straightforward. You might find it like really daunting, but yeah, like take it slowly. This is probably because it's the first time, but as you experiment with more models, as you train more models, you probably get used to these kind of things. So we have used a network of one hidden layer. M is reasonably small data sets, but let's say you could increase the size of the network to maybe 300 layers, and probably using the any dimension you want. So can you do it? Can you build and train this new network? What does this change on the overall performance? Also, I want you to go to PyTorch image augmentation function and explore different augmentation function available, and then try to include them in the model. Yeah, so try to include them in the model and see if they make a difference. One thing for sure is that augmenting image will improve the performance if done in the right way. Yeah, so experiment with these things. Try to use augmentation and see if they make significant improvement to your model. This is it about the homework workflow. So in most homework, you'll be doing these steps. So you'll be creating a data loader. Um, After data loader, you'll be training a model. You'll be evaluating the model. You'll be closely watching how the model is performing during the training. So you'll be using a weight and bias for many assignments. And then after that, you'll be testing your model on unseen datasets. And yeah, so thank you so much. If you have any question, please feel free to reach out.